AI is disrupting virtually every industry as we know it. However, AI models can be biased. That means billions are being treated unfairly on the basis of their race, age, gender, and more. So we need to reinvent how AI is used for societal impact, especially in fields like healthcare. For example, the data used behind the technology and algorithms have been heavily geared towards white patients. For historical reasons, there are some minority groups for which there is not much data available. So training datasets are not representative of the entire population, and models appear to be accurate overall simply by performing well for the majority only. So our team, Equalmodel, has implemented moment multi-calibration, which, unlike many other fairness algorithms, makes sure that an ML model will be equally confident and accurate about any subgroup and provides uncertainty estimation. Now, what is moment multi-calibration?
So calibration is a simple statistical sanity check that actually comes out of the weather forecasting literature. So when a weatherman says there's a 10% chance of rain, what does that mean? Well, to check if he's calibrated, what you want to check is that on all of the days on which he predicted there was a 10% chance of rain, it actually rained 10% of the time. On all of the days in which he predicted there was a 20% chance of rain, it actually rained 20% of the time, and so on. So it's this simple sanity check. And you can ask for calibrated predictions not just for weather, but for all sorts of predictive tasks that might have important consequences about people. So for example, if I'm predicting whether someone is going to show up for a parole hearing, and making parole decisions based on this, I might want my forecast to be calibrated. If I'm trying to predict in a medical context someone's reaction to a drug, I might want my forecast to be calibrated. But when you start making predictions about people, simple calibration really isn't enough, because calibration is really an average statistic, averaged across many, many, possibly very different people. So if I say that 20% of the people for whom I predict will have a, bad reaction to a drug when I predict 20%, that's averaging over many very different people. And it might be that my predictions are no longer calibrated when I zoom in on some medically relevant demographic group. And so multi-calibration asks for something much stronger. It says, well, you tell me all of the possibly very many different intersecting demographic groups that you care about, and I will provide a prediction for you that is calibrated not just on the whole, enormous population of people, but also simultaneously on each of these demographic groups when I zoom in. And so multi-calibrated predictions can be informative for particular groups of people in ways that simple calibrated predictions can't be. And once you start doing that, you can go even further, right? Calibration is just about getting averages right. But in important contexts, like in predictive medicine, we also care about the uncertainty of our forecast. And so you can generalize this idea of mean multi-calibration to higher moments as well. I can ask that the variances of the residuals of my predictions be calibrated in a particular way, and that they can be multi-calibrated. And doing this allows individuals from these different demographic groups to be confident not just in the average of their prediction, but in the uncertainty of the prediction as well.
There are two main parts of the algorithm. In fact, think of it as a game with two players, an auditor and a fixer. The goal of the auditor is to find the points in the dataset on which the model is not performing well. We can either manually predefine some groups for the auditor to check, such as race or gender, or we can use a component of the algorithm called the learning oracle that can learn which points will have bad predictions, and it will send those to the auditor. The auditor then checks some fairness criteria for the subgroup, and if there is a violation, it will pass that to the other player, which is the fixer. Now, the fixer has two tasks. It will first adjust the prediction made by the model by some amount, then it will store the subgroup that the auditor gave to it and the modification that it applied. That is, it's going to remember its action. The interaction between the two players continues in multiple rounds until convergence. That is, when the auditor can no longer find points whose predictions are violating the criteria. This entire process or game between the two players is called mean multi-calibration. What this means is that for all subgroups that we defined, if the true outcome is close to some number I, the predicted outcome is also close to I. Now, the reason why this is important is that we don't want the model to do well just for females or just for African Americans. We want the model to also perform well for people belonging to multiple groups at the same time, such as a person who identifies as African American and female.
The next component we have in our algorithm is called moment multi-calibration. Since the mean is the first moment, this part of the algorithm focuses on calibrating the second moment, variance. It will go through the same process as mean calibration, whereas the only difference is that it uses a variance predictor. So instead of predicting the expected y given the data x, here the predictor predicts how uncertain y is. And ultimately, the last part of algorithm is called alternating gradient descent. It combines the updates of the mean and the moment prediction in one process. So after the auditor and the fixer ensure each subgroup is mean calibrated, they switch their focus to moment calibration. As the name suggests, the auditor and the fixer alternate their focus on mean prediction and the moment prediction until convergence. And based on both theories in our experiment, this process can stop within a finite number of steps. So after all, what do we achieve at the end? Not only do we get fairer predictions for each subgroups, but also we're able to estimate how uncertain each prediction is, making the model more informative and interpretable.
To test our implementation, we used Safari 10, which is a multi-class image dataset. The use of Safari 10 was motivated by the need for very large datasets to avoid overfitting in our algorithm. There are 10 classes, ranging from airplanes to trucks, and the initial machine learning model's task is to predict whether the object in the image can fly or not fly. Notice how there are automatically some subgroups or demographics that can be identified. For instance, the automobile and airplane are not animals, but birds and cats are. Now this can implicitly introduce some bias into the model. Our next step is to train a machine learning model on this dataset that will act as the base input into the algorithm. And finally, we'll feed in our trained model into the moment multi-calibration algorithm.
Now that we understand the structure of our data, we can take a look at its results. Here we can see graphs depicting the predicted and true variances of a subset after each iteration of alternating gradient descent. We can note that in both the validation and test dataset, the predicted variance converges towards the true value after very few iterations. Functionally, this means that our algorithm is providing underrepresented populations with the variance they are meant to have, leading to a greater degree of confidence when making predictions on these demographics. This third graph actually depicts some interpretable predictions on varying demographics, showing both the prediction on each data point and the confidence interval surrounding it. In addition to its confidence guarantees, we've been able to run this algorithm in 5 minutes or less on each dataset and model tested with only moderate, if any, degree of hyperparameter tuning needed. The results also preserve privacy on data since we post-process on predictions and a model rather than on raw data itself. This makes it HIPAA compliant in the healthcare case. And while accuracy as a metric for scoring fairness is flawed, particularly in datasets that overrepresent certain demographics, we found that the accuracy after post-processing on predictions with Equalmodel is still within 5% of the original model. This acts as a good litmus test to assure us that this model is performing well, as it's never been implemented before, so there's not a lot of established benchmarks for comparison. For anyone interested in taking a more direct look at the code or hoping to experiment with it on their own, we're happy to announce that we've posted it to a publicly available GitHub that you can access at the following link. We've also attached a README detailing exactly how to use Equalmodel.
Now we hope to look ahead. With our state-of-the-art algorithm, we have the potential to disrupt the entire AI industry. We, as Equalmodel, hope to empower firms to make a societal impact in an ethical manner with no persisting bias. This can range from making a drug dosage algorithm more aware of its confidence in its predictions to ensuring that all applicants get a fair loan risk score. Clearly, our product can touch innumerable models. We hope to ultimately provide Equalmodel as an AI-as-a-service product, such that our model can be easily mounted onto a firm's proprietary algorithm with just 2 lines of code. Now, before we end, we want to close with a quote. With great power comes great responsibility. AI is not an exception. We will disrupt the AI industry such that firms will strive towards ensuring more fair and equitable outcomes for both you and I.